Today, we want to continue our discussion of vectors. And we're going to start with these two vectors. U is -3, 4, and V is 2, 1. So I've drawn a picture of the vectors U and V. And I want to find these vectors. I want to perform some operations on vectors. That's kind of our thing for today, operations on vectors. You know what? I am going to talk about components as well. And we were already started talking about standard position. So I haven't told you how to add vectors except geometrically. So the vector U equals -3, 4, and V equals 2, 1. If I want to add those vectors, I can put a copy of V at the end of U, or I can put a copy of U at the end of V. Makes sense. We're calling something addition. It should be commutative. We like our addition to be commutative. We're okay if our multiplication isn't commutative, but we like our addition to be commutative. So I can either put a copy of V at the end of U, or I can put a copy of U at the end of V. And then that's creating a little parallelogram. And so if I just go to where they meet, that's going to be the vector U plus V. Now, this is how we do things geometrically. We also might want to know just if I want to take U plus V, if I don't have a picture. Now, I didn't talk about how to do vector addition in this way, mostly because I don't have to. What you think would happen, what you think you would do is exactly what you do. -3 plus 2 is -1. 4 plus 1 is 5. And now take a look at our picture. That U plus V is at -1, 5. It's always great in math when what you think should happen is what happens. You want to add a couple of vectors and you have them have their components, add the corresponding components. It's just as you had suspected. I love it when math is like a Scooby-Doo episode. Super obvious right from the beginning. The same thing happens if I want to multiply -2 times V. So if I want to do -2 times V, I want to take the negative will change the direction of V, and the 2 will stretch it by a factor of 2. So I'll take 2 copies of V. There's 1V, and then there's 2V, and it's going in the opposite direction. So there's the vector -2 times V. It's twice as long and pointed in the opposite direction. Now we got to think about what we're going to do with components. If I take a -2, a scalar, and scale up the vector 2, 1, if you guessed that we should have -4, -2, you are correct. That's exactly what we do. That's how we multiply a vector by a scalar. -2V is -4, -2. And then I have U minus 2V. That could just be taking a copy of 2V and putting it at the end of U. Or I could put a copy of U at the end of -2V. And that makes this parallelogram. And there's the vector u minus 2v. And if I have components of u minus 2v, I have negative 3, 4 minus 2 times 2, 1. Now here I have some addition and some multiplication. So we have to think, well, what are we supposed to do? We do the same thing that we always do. Multiplication goes before addition. The order of operations is always in effect. So this is going to be negative 3, 4 plus negative 4, negative 2. I multiply the second one by negative 2, and then I just add the components, multiplication, then addition. So negative 3 minus 4 is negative 7, and 4 minus 2 is 2. And that is right where u minus 2v lands. It's at negative 7, 2. Note that the other thing we can do is we can also read this u minus 2v. I could, at the end of u, put 2 copies of negative v. When we add multiple scalar multiples of vectors, we're creating what's called a linear combination of vectors. So when we do scalar multiplication and vector addition, we're finding linear combinations of vectors. So u minus 2v is a linear combination of the vectors u and v. So u minus 2v is a linear combination of u and v. The reason I define the term linear combinations is because I'm going to call these linear combinations. It's a term from linear algebra, and I don't think it shows up in trigonometry, but it does if I'm in charge, because every summer I've been teaching a linear algebra class for like the last 10 years, so it's become kind of a habit. I can't not do it. So y'all are gonna have to learn that term, linear combinations. It's just when we do scalar multiplication and vector addition to combine some vectors, we're making what's called a linear combination of those vectors. Any questions? All right. Let's talk about components. U is still going to be negative 3, 4. That's bad grammar. U are still going to be negative 3, 4. And V will still be the vector 2, 1. So these are the components of the vectors. So -3 is the horizontal component of u. And 4 is the vertical component of u. Of u. So we have horizontal and vertical components. In standard position, we have the initial point at the origin and the terminal point determined by the components. So the vector u at -3, 4 oh, you just changed color from the top page, the part of the page, to the bottom part of the page. Here's our -3, our horizontal component, and our vertical component is 4. So here is the 4. Just like with points, coordinates. So, but we're interpreting this and not as a set of coordinates, but the components of a vector, not the coordinates of a point, but the components of a vector. Here's u in standard position. When we first started talking about vectors, we mentioned that vectors have magnitude and direction. Magnitude is just the length of the vector. And so if we look at this vector as the hypotenuse of a right triangle, we could just use the Pythagorean theorem to find the magnitude of the vector u. So our notation for this is the absolute value of u, but we're not going to read it as absolute value. We're going to say the magnitude of u. It's one of those things we start writing it and we don't know what to say until we get to the thing in the middle. So we write this vertical bar, and I go, is this absolute value or magnitude? And then we write the u. It says that doesn't tell us anything. We put the vector on top of u and say, u is a vector. We're going to say magnitude of u. So you don't say it until this arrow shows up. That's when you know it's a magnitude. If the arrow didn't show up, we would just say absolute value of u. Secretly, we could also just say the magnitude of u. But that's okay. Let's keep things separate. We're just going to use the Pythagorean theorem, and the magnitude of u will be the square roots of -3 squared plus 4 squared, which is the square root of 25, which is 5. So we'd say the magnitude of u is 5. That's the length from the origin to the end of u. That's so threatening, the end of u. You know what I mean? All right. a vector has magnitude and direction. So we are going 5 units. We have to describe the direction in some way. For our direction, we want to measure a direction angle. Now, there's a lot of places that we can measure this direction from. In fact, we have an uncountable infinity of choices, but there are only a few that make sense, and we're going to pick one as standard. So our direction is going to be the angle from the positive x-axis. So our direction angle will be measured from the positive x-axis, where counterclockwise is positive. This is the same direction angle that we were using before. We were starting at 0 degrees at the positive x-axis and going counterclockwise into positive angles. So let's figure out that calculation. I also conveniently ran myself out of space. So the vector is still u, -3, 4. It's still in the second quadrant. And I'm going to keep its color as purple, since that's the new color for u. Had to be purple because it's made up of red and blue components. So the angle that we're looking for is going to be this angle here. So we know that the magnitude is 5. To find theta, we're going to pull out this right triangle. The reference angle for theta is the angle between the terminal side and the nearest x-axis. So if we pull out this triangle, we're looking for this angle, which will be the reference angle. Since the components of u are 3 and 4, this side adjacent to theta, the reference angle is 3, and the side opposite is 4. So for the reference angle, we'll use tangent inverse. And opposite over adjacent. We grab our calculating machine. We make sure we're in degrees. And we find the tangent inverse of 4/3. 53.1 degrees. Now this is the reference angle. So we have to put it in quadrant 2. So the angle theta is 180 minus 53.1. Any questions? So this is a similar game that we've played before. Find a reference angle, put the reference angle in the appropriate quadrants. Here we knew what quadrant to place things because we had the components of u. The components of u were at -3 and 4. That we recognize as being in the second quadrant. So when we find the angle theta, we'll get a 53.1 degree angle in quadrant 2 or 126.9. Now, you might read the 3 adjacent side 3 as -3. Which is fine. You might read the opposite is 4 and the adjacent side is -3. And we're looking for this reference angle. The problem is if we use tangent inverse, if we find the tangent inverse, not really a problem as long as, actually it's not a problem at all, as long as we keep our wits about us. If we do tangent inverse of -4/3, if we do the tangent inverse of 4 divided by -3, we end up with -53.1 degrees. This is because tangent inverse is set to use quadrant 4 as the negative quadrant for tangent. So tangent inverse of a negative number will show up in the fourth quadrant. The first quadrant is always positive, and so we use the fourth quadrant for tangent as the other positive part, just like sine. Sine is set up to return angles between -π/2 and π/2, between -90 and +90. So the -53.1 is going to show up in the fourth quadrant. And if we just flip it over into the second quadrant, to move an angle into the next quadrant, from the fourth to the second, we can just add 180 degrees. And check it out, it's the same calculation. So what we punch into our calculator is not as important as keeping our wits about us and knowing where our vector is supposed to be. Any questions? All right. The useful thing about components is it helps us break down into pieces what's going on. So for example, if I'm pushing, if one person is pushing on an object at 3 units horizontally to the left, and someone else is pushing this object 4 units up, then we just make a component vector of moving 3 units to the left. We just make that into a vector of -3 in the -3, 0, and the up pushing 4 up, we just make that a 0, 4, and find the resultant motion. So we just imagine if one person is pushing on the block 3 units with a strength of 3 units to the left, and another person is pushing on the block at a strength of 4 units going up, then the result will be moving at 5 units at an angle of 126.9 degrees from standard, from the positive x-axis. Where we might need components even more is to think about what would happen if one boat, 2 tugboats. One is pulling at, let's say, a 2-2. And another tugboat, rather than just lining up the tugboats, I guess, and pulling each other, they want to waste some of their effort. So the other tugboat is pulling at 3, -1. We can figure out what direction these boats will be hauling their barge. So 2 tugboats in a tug of war, the resultant vector, by just adding the 2 vectors, u plus v, that will be the direction that the barge goes. So at the end of v, I'll just put a copy of u. And we can see that the barge will still be moving to the left. The barge will still be moving to the left, but u is pulling it a little bit up from v. So it's pulling a little bit up from the center line. It's not exactly going along this center line. And so the whole time the dockmaster would be like, "Oh, guys, get it together." That's right. The tug crews here are from different unions. Then the 2 different unions realize that the boss is playing them against each other. Then they form a bigger union. Any questions? All right. So what we want to be able to do is take a vector and describe it with components. We also want to be able to take a vector and describe it with a magnitude and a direction. And that will be in the form of, the magnitude will just be in the form of a length, and the direction will be measured with an angle. The standard way to measure an angle is to measure it from the positive x-axis and counterclockwise is positive. But there might be a different way of measuring. So for example, measuring a heading might be measured clockwise from north. So if a boat is traveling 30 degrees east of north, that means you start off at north and spin 30 degrees east, which would be in the clockwise direction. So unless otherwise stated, start measuring from the positive x-axis. Counterclockwise is a positive angle, or just see how the direction is described. So is it 30 degrees north of east or 30 degrees east of north? That'll tell you where the start is and which direction it's pointing. We want to be able to go from one to the other. Given components, find magnitude and direction. Given a magnitude and direction, find the components. Any questions? Now, at this point, you might be thinking, dude, you sound like you're going into wrap-up voice, and yet you have not told us how to go from magnitude and direction to horizontal and vertical components. And we've only done one example of going from horizontal and vertical components to magnitude and direction. And I'm like, oh, that is correct. I did not tell you how to get the components from the magnitude and the direction. That's because secretly, you already know how to do it. Your job is to think about what I'm asking you to do, and then take what you already know how to do and figure it out. Fortunately for our heroes, we'll come back on Tuesday and find out how it went. So if you're like, oh, dude, I could not get that, I'll be like, oh, well, here's how it goes. And then you're going to be like, oh, dang, that's what I thought should happen. I was going to try that, but I didn't. And then I'll be like, oh, well, next time you're going to try it, aren't you? Because what's the worst case scenario? You get it wrong. It's like, oh, no, that's not how it works. Here's how it works. Don't be afraid to make a mistake, I guess is my point. We got to stop making people afraid to make mistakes. We need to start celebrating mistakes. Because in any endeavor, we're trying to figure stuff out. The most important thing to do is something. Can't win if you don't play. Lottery philosophy. Any questions? Comments? Deep thoughts? All right. That's going to do it for today. That's going to do it for this week. I'll see you all on Tuesday. Everybody have a good weekend, and thanks for playing.